All right. So this will be AP Chem Notes, pages 48 and 49. And we're starting a new section. In our book, it's chapter 11. But more importantly, it is a unit on rates. Now, by rate, you can just think speed, how fast something occurs. So we're going to be looking at how fast reactions occur. And I find that AP chemistry students usually don't like this unit at first. And my suspicion is it's because we don't do much of this in first year chemistry. We barely mention it. One of the reasons we don't do much is just because we just don't have enough time to do everything. Another is because it gets a little bit complicated and we don't feel it's worth the effort until you get to AP. So don't be surprised if you have to fight a little bit harder in this unit just because it's going to be more new material than what we've been seeing lately. Okay, so regarding rates, we have what's called the average rate. We also have what's called the instantaneous rate. So the difference between these is the average rate would just be over a certain time period, but the reaction would have different rates at different moments. So for example, if we take a look at this graph here, this particular reaction was studied starting at 0 time and going to 24 hours. And over this period of time, you can see, my guess is this reaction is the decomposition of hydrogen peroxide. And over this period of time, you can see how the concentration changed. And you can see at the very beginning, let me zoom in on this so we can really analyze this. At the beginning, if you look at this line that was drawn here, I'll draw new lines. The change in concentration was pretty severe. But then over a later period of time, you can look at this line here, the change in concentration was not as severe. It's still decreasing in concentration, but not as fast. And then down here at the end, it's still decreasing, but even slower. That wasn't a very good line. Let me do a better one there, like something like that. We're barely sloping at all. So what they mean by average rate is what was the rate from the beginning until the end. The rate was changing the entire time. In this case, it was slowing down, which is pretty typical. So that's what average rate means. Now, an instantaneous rate means what's the rate at an exact moment in time. So let's say a problem said it wanted the instantaneous rate right. It's hard to tell where they picked, but let's say they said the instantaneous rate right here. One way to determine that is to draw a tangent line on the curve. So the author of this has already done that. And if I copy it, it would be right about there. And so what we could do is we could draw this tangent line. We could then find the slope of that line. And that slope would be the rate, or more importantly, it would be the instantaneous rate at that moment. But notice that rate, that's not the correct rate at the beginning. It's not the correct rate at the end. It's probably not the correct rate at any other time other than that moment. Now, what this brings up is not only the difference between average rate and instantaneous rate, but this also brings up This is where calculus can come in and be very useful, because calculus is the study of how things are changing. And so what you could do is you could use calculus to solve problems like this for the instantaneous rate, but we're not going to use that in this class. I just like to mention that this is where things like that are useful. We are mainly going to focus on average rates. So we'll just be looking at what's the rate over a certain period of time. We will not be concerned about instantaneous rate under normal situations. Okay. Looking at letter C, I've seen this chart called a variety of different things, but for our cases, we will call it a reaction energy profile. And I did a short review of this when we were at the beginning of the thermochem unit, but let's go through it again. I've got energy or enthalpy over here. So you see this one says enthalpy, this one says energy. And then going to the right on the x-axis, basically that's just the reaction occurring. So this person labeled it reaction coordinate. This person labeled it progress of the reaction. And what this shows is as the reaction occurs, it shows the change in enthalpy. So in this case, reactants here, products are higher. So that means there was an increase in enthalpy. In other words, this is endothermic. This other one over here, the reactants are here, products are lower. So the change in enthalpy was that. So this would be exothermic. Other interesting things to note is how high the hill is. So in this first one, the hill goes from here, the reactants, all the way up there. That's what we call activation energy, and the symbol's EA. In the second one, the hill would be all the way up to there. And that would be the activation energy. And that's the energy that's needed as the particles collide. They must collide with that much energy or more in order to go through the different transitions that must happen to make its way over this hill and then finish the reaction. Now, there's a variety of interesting things about this chart to talk about. First thing to notice is that delta H, the enthalpy, has nothing to do with the hill at all. The only thing delta H cares about is where you start here and where you end here. What the hill looks like, whether the hill has one hump like on the left or two humps like on the right or 50 humps, it doesn't matter. All delta H cares about is where you start and where you end. In many ways, that's another way of saying Hess law. It doesn't matter how you get there, the energy will be the same. Activation energy is kind of the opposite. Activation energy is all about the curve. It's all about how high the biggest hump is, which in this case is the only one. And in the one on the right, it has two humps. Now, what those represent are just two important steps in this reaction. And the reaction can have many steps in the middle, and chemicals that exist for just a fraction of a second during the reaction are called an intermediate. They're not reactants, they're not products, they're hidden inside the arrow when we typically draw a reaction out. And you'll see that mentioned numerous times this unit as intermediate. So again, those are things that only exist for a moment in between the reactants and products. And this chart here shows that one would exist right here in this area. Well, that was way too big. Let's do a more careful job there. So right in this area here. And then these two humps would be transition states. So this would be transition from reactant to the intermediate, the first one. And then the second one would be a transition state from the intermediate to the product. There's more to talk about with these charts and catalysts, but I'll save that for when that comes up later. All right. Regarding reaction rates and concentration. Well, as a reaction occurs, we have reactants turning into products. We'll just not even worry about the reaction going backwards right now. Of course, as the reaction occurs, the reactants are going to go down in concentration. The products are going to go up in concentration. So we could monitor the speed or rate of reaction by looking at the reactants disappearing or the products forming. We typically look at the reactants. So you'll see, to monitor a reaction, we do something called a rate expression. And the rate expression allows us to mathematically monitor how fast a reaction occurs. And in this case, if you look at my example, I have chemical A, chemical B, chemical C forming products. And the rate expression is rate equals a constant that we'll talk about, the concentration of the first chemical to the M, the concentration of the second chemical to the N, the concentration of the third chemical, all of these are reactants, A, B, and C, to the P. Now notice, typically, you would expect the coefficients to be in there, like if we were doing equilibrium, but that's not the case. So notice this right here. The coefficients do not go in the rate expression. Coefficients just have to do with stoichiometry, and they do end up affecting other things, but they do not play a role here directly. So that's why this has a little M, a little N, and a little P. And what those are is they are called orders. And simply, an order is how critical is the concentration of that chemical on the rate. In other words, does the concentration of that chemical affect the rate at all? Does it affect it a little bit? Or does it have a dramatic effect? Now you'll notice the letter O was not used because it looks like a 0, and that can get confusing. So often when this is taught, people use M, N, and P or something like that. And again, I have to emphasize, I know you look at coefficients all the time. You're always taught, balance the reaction, look at the coefficients, always look at the coefficients, stoichiometry. Right now, don't look at the coefficients. We don't need them. Now, regarding orders, I want to talk about this here. If a chemical has an order of 0, that says the rate of the reaction is not based on the concentration of that chemical. In other words, the chemical needs to be there, it needs to be present, but its concentration will not affect the rate. So again, rate is independent of concentration of that chemical. If a chemical has an order of 1, this is what you would expect. This would be the common sense situation. Then the rate of the reaction is directly proportional to the concentration of the chemical. So in other words, if you double the concentration of the chemical, the rate will double. If you cut the chemical's concentration by 10 times, then the rate will be cut in rate speed by 10 times. And then we have ones that are more extreme than that. For example, you can have an order of 2. In this case, the rate is proportional to the concentration squared. So this is a very dramatic situation where the concentration really affects it. Now at this point, you're probably thinking, well, why is this? Well, I hope you're thinking this. Why is it that some things have an order of 0, they don't affect the rate? Some things have an order of 1, which is what we would assume, and something has an order of 2 or even higher. It's possible. It all has to do with the magic that's happening inside the arrow. It all has to do with what collisions are happening, what the energies of those collisions are, which one is at the top of the hill, and so on. And so I can't really get into why things have an order of 0 or 1 or 2 until we really take a look inside the arrow, and we're going to do that soon. That's going to be called the mechanism. And once we look at the mechanism, then we can actually explain and show why something has the order it does. But for now, I'm just going to either tell you what the order is, or we're going to solve for it experimentally. Now, there's also, sometimes you'll be asked for the overall order of a reaction. That just means to add up every order of every reactant. And it just kind of gives you an idea of how sensitive the reaction is to concentration changes overall. Now, the first way that we are going to look at determining the order I'm moving my pages around in a way that I don't want. Let's just go with it. Oh, I've created a monster. All right, this is better. The first way that we're going to take a look at how to determine the order of a reactant, or how to determine the entire rate expression, which includes the order, is this one here. It's called the method of initial rates. And what it requires you to do is you have to get a bunch of experimental data. You take your reaction of interest and you run it, and you see how fast it goes at certain concentrations. And then you take one of the chemicals and you cut its concentration in half, for example, and you run the reaction again and see how fast it goes. And then maybe you go to another chemical and you cut its concentration in half and see what that does. And so by changing one chemical at a time, you're able to see what effect it has on the rate. Now, once you get the data, what you do is you take one of your trials, which I'll call rate 1, and compare it to another trial, which I'll call rate 2 in this case. And what you'll see will happen is a bunch of the numbers will cancel, and it will actually allow us to solve for the order of hopefully one of the chemicals. So take this situation here. So the reaction has 3 reactants, KO2, H2O, and CO2. And again, do not look at the coefficients. 4, 2, 4 is not of a concern right now. I know that feels awkward because you've always been told to look at coefficients. What I want to do is I want to get the order of all 3 reactants. In other words, we know they're going down in concentration, but I want to know what effect their concentration has on the rate. I want the overall rate expression with the orders in it. I want to solve for K, the rate constant, and then the overall order is really easy. So we have this data, and it's quite a big chunk of data. Somebody took this reaction and they ran it 4 different times. Listed here is the concentration of each chemical, the reactants. That was at the beginning, and then they determined the rate. Now in this case, they determined the rate in molarity per minute. In other words, this is how fast the molarity of the chemical was going down every minute. And again, it's going down because of these are the reactants. Now I made a note here. Sometimes the numbers make it obvious. So if you look at this data and you look at these numbers here as they change, and these numbers here and these numbers here, I don't think this one's obvious. It's hard to look at these sets of data and see what the change in concentration is doing to the rate. And that's on purpose, because I want to force this particular example. However, sometimes it is obvious. In other words, what you'll see is let's just say chemical A is forming chemical B. And what you'll see is an experiment is done where chemical A is, let's say, 0.10 molarity. And then another experiment is done where chemical A is 0.20 molarity. And the rate, for example, I'm just going to make up some numbers here. The rate under the first situation, let's just say, is 5. I'm not even going to worry about units. And the rate in the other situation is 10. Well, this one's just obvious. If you double the concentration and the rate doubles, then that means that chemical A must be first order, a direct proportion. Likewise, let's say that we saw this. In this case, if we double the concentration of chemical A, but the rate stays the same, that means that chemical A must be in order of 0. And it's going to take a little practice to get used to this concept. But anyway, that's what I mean by making it obvious. I don't think these pieces of data are obvious. So what you do is you compare any two experiments. Now, the first one I chose to do is I chose to compare experiment 1 and 2. You don't have to do 1 and 2, but I chose 1 and 2 because only one chemical was changing. The KO2 didn't change. The CO2 didn't change. The only thing that changed was right here, the water. And so by finding two experiments in which only one chemical change will allow us to find the order of that one chemical. So I wrote out the rate expression for experiment 1. So again, rate, constant, each concentration of reactant raised to its order, which we don't know the orders yet, so I called them M, N, and P. Did the same thing for experiment 2, 9.99, constant, concentrations raised to their orders. And what happens here is you get to cancel a lot of stuff. We don't know what the K is, but whatever it is, it's the same thing, so that cancels. We don't know what M is, but it's going to be the same, and 0.15 is the same, so that cancels. We don't know what P is, but it's going to be the same, so that cancels. And so now, if you take 11 and divide by 9.19, you get 1.2. I've got 0.6 over 0.5 to the n, and I'm solving for the n. And it turns out that this one's obvious. You end up getting 1.2 equals 1.2 to the n. So n is a 1. So the order of water in this reaction is an order of 1. So we now have that one solved. Now, let's compare experiment 3 and 4. If I do that, I end up with experiment 3 here, experiment 4 here. I'd recommend you pause the video and make sure that you understand where all the numbers came from. And then once you're satisfied that you're happy with where these numbers came from, you can then continue. Notice for the water, I went ahead and put the 1 in. I know that it's a 1. So don't call it N anymore, call it what it is. And in this case, if the water's changing, notice it's going from 0.5 to 0.3, that's not a problem anymore because we now know what its order is. All right, the K's cancel. The first chemical cancels. If you take 2.81, divide by 5.67, and then factor in the 0.5 and the 0.3, mathematically you get this. You get 0.2974. I kept an extra sig fig. And then over here, this section, I just kept as it already was. So 0.15 over 0.275 to the P. Now, when you do the math on this, it comes out a little bit messy. You get 0.2974 equals 0.5454 to the p. Now, one technique you can try is you can just try raising 0.5454 to a variety of exponents, and you'll get lucky eventually, and you'll find that it's a 2 or second order. But there's a more direct mathematical approach that I actually have at the top of the notes. When you get to this situation, take the log of both sides. Excuse me, the regular log. When you take the log of this side, you get negative 0.5267. On the other side, you get negative 0.2633, and the log of the exponent p is just now regular p, and so this is easier to solve for. You just divide the negative 0.2633 and you get a 2. So that can be a mathematical shortcut to solving it without just doing trial and error over and over again. Now at this point, we now know the water is an order of 1. And we know that the CO2 is an order of 2, and now we just have to do the last one. In this case, I compared experiment 1, experiment 3. Still don't know K. Plugged all my numbers in. When you do the math, you end up getting this situation. And this one ends up being a 0.599 to 0.6. So in this case, you just use common sense and simple rounding. You can see it's 1. So now that I know the orders of every chemical, I can write the rate expression, and that I have here. We'd say the rate of this reaction is equal to a constant that we still don't know, but we'll soon. The first chemical, KO2, to the first order, because we solved for it. The second chemical, I really should be saying reactant, the second reactant to the first order, and the third and final reactant to the second order, which basically all we really solved for so far is the orders. But that's most of the work. Now that I know those, what you can do is you can take any one of the experiments, plug the numbers in, and solve for K. So which one did I use? 5.67. So I used experiment 4. You can choose any of the 4 experiments. It doesn't matter, but I just randomly picked number 4. I plugged in the rate, the initial concentrations, the orders, did the math, and you get a K of 1.00 times 10 to the third. And then the units, in this case, end up being molarity cubed per minute in the denominator. Or you might see it written this way, molarity to the negative third, minute to the negative third. Or if it really gets weird, you might see it where they break molarity into its pieces and you get this liters cubed times molarity to the negative third times minutes to the negative 1. And that's just obnoxious because it's hard to tell what it is. But be aware, you might see some of these weird things. What we now need to talk about is why is the unit such a weird situation? All right, so take a look at the rate expression that we just wrote out. You could either look up here or you could look down here where we did it with the numbers. And let's just look at units. We know that the unit of rate is molarity per minute. That was given in the data table up above. We know that each reactant is molarity raised to its order. So the first reactant's to the first order, second to the first order, and the last one to the second order. What we're solving for is what must this unit be so that when everything on the right of the equal sign is multiplied, you get molarity per minute. Well, there is no per minute in the reactants. So the only way I'm going to get per minute is if I add it. So at this point, I know that I have to do per minute for my constant. Now, if all I did was per minute, we would have molarity to the first times molarity to the first times molarity squared, and that would give us a rate of molarity to the fourth per minute. And that doesn't make any sense. We don't want to measure how fast a reaction occurs in molarity to the fourth. That's weird. We want it molarity per minute, kind of like miles per hour. If you're driving your car, you don't want to measure the speed of your car in miles to the fourth per hour. You want something simple like miles per hour. So we don't want this. So what we have to do is we have to get rid of all the molarities except for one. And so the way you would get rid of this is you would do a molarity to the third on the bottom, and that would get rid of all of them except one. And that's why I have a unit of molarity to the third times minutes as a denominator. And you can check it. What you can do is you can take what you think is the right unit, so molarity cubed times minutes, multiply it, this would be K, times all of your concentrations for your chemicals. And it should come out to be molarity per minute and match what the rate in the data table says. And in this case, it does. If it doesn't, then you made a mistake. What some students do is they know, just add up these and subtract one, and then put that on the bottom. And that does work. You're getting the right answer and you don't really know why, but it does get you the right answer. I would rather you understand what you're doing. And the last question that I asked was the overall order. You just add up the order of every chemical. So 1, 2, and the third chemical. Again, I really should be saying reactants. You add up the order of every reactant. In this case, you get a 4. All right, I mentioned this earlier. Sometimes you can tell the orders by looking at the changes. So here's another example where the data is a lot easier to work with. You can see that A isn't changing from experiment 1 to 2, so we can ignore it. B is doubled. And if B doubles and the rate doubles, that means that B must be an order of 1. So if the data is easy like this, don't go through all this math that I just showed you. Just use logic. If the data is not so easy, you kind of have no choice but to go through the math and figure it out. And that takes care of the notes up through page 49.